Today's tutorial is about the selectivity of the bromination with NBS and bromosuccinimide. This is much easier to handle and much safer to handle compared to elemental bromine, of course. And as a substrate, we will choose this isobutyl benzene. For a radical reaction, for instance, with AIBN as radical reaction starter, just heating up and the first radicals will be formed by thermal decomposition of AIBN. We would then anticipate that we would obtain either the product with the bromine in benzylic position or the product with the bromine at the tertiary position. Since the intermediary radical is much more stabilized in benzylic position due to the conjugation with the benzene ring, this will actually be the main product, and it has been isolated with an excellent yield of 95%. If we change the reaction conditions to acidic conditions, for instance, by adding catalytic amounts of protons, for instance, from sulfuric acid, then we would protonate in the first reaction step the NBS, and the NBS would be protonated not at the electron pair of the nitrogen, but at one of the oxygens. And this will then activate the bromine. We can visualize that easily by drawing a mesomeric structure with a positive charge at the nitrogen. The nitrogen is a priori already much more electrophilic than the bromine, and a positively charged nitrogen even more. That means that that electron pair is polarized to the nitrogen, and we have a very much positively polarized bromine, and this means this is electrophilic. And indeed, it is electrophilic enough to attack that aromatic ring, either in ortho or in para position. Since the isobutyl group is a rather bulky one, the para position will be preferred, and this means that as the main product, in this case, we will obtain the brominated product in the 4 position. So now we know how to brominate in benzylic position. We know how to brominate here at the aromatic ring, but what about the bromination here in this position? Well, the direct bromination won't be possible, but With a simple retrosynthetic analysis, we can figure out a way to synthesize this product. Rather simple is the functional group interconversion from the alcohol to the bromide simply with adding HBr. But how can we synthesize this tertiary alcohol? In my opinion, the best way should be starting from phenyl acetic acid ester, for instance, the methyl ester, and treating that with two equivalents of methyl magnesium bromide. First equivalent, addition, elimination, then we are at the oxidation state of the ketone, and the ketone will then react with the second equivalent. Okay, so then we have the alcohol, and which we can then treat with HBr to get to the final bromide. Some of you might have the idea, why not starting with a benzyl Grignard and let this react with acetone? Shouldn't that be the cheaper and more straightforward method to get to the tertiary alcohol? The problem is how to synthesize the benzyl magnesium bromide, because it is well known that treating benzyl bromide with magnesium will lead preferentially to the 1,2-diphenyl ethane, simply because in Grignard reagent formation we have radical intermediates, long-lived radical intermediates as a benzyl radical, and they live long enough to get together and form the CC bond. So it's rather complicated to synthesize this benzyl magnesium bromide. It is possible with some tricks, but this way, with the methyl magnesium bromide, would be much easier. Thank you for listening. See you next time.